Hi, my name is Daniel Cummings. I'm with Intel Labs, and I'm presenting my co-author's work called A Hardware-Aware Framework for Accelerating Neural Architecture Search Across Modalities that was accepted as part of the AutoML Conference workshop track. As an overview, we start by noting that the DNN design process is tied to the hardware platform that is available to the researcher at the time. And latency characteristics of DNNs can change drastically between hardware platforms. Thus, by saying hardware aware, we're really emphasizing that multiple objectives such as, say, top one accuracy and latency should be treated as optimization objectives. So in this work, we leverage one-shot supernetworks to enable the efficient exploration of latency optimal architectures. Next, we note that many research efforts have focused on image classification, but it's really important to understand how NAS approaches translate to other modalities. And so to enable the exploration of these questions, we start by showing a generalizable NAS framework that offers a variety of search algorithms and performance predictor solutions. And we also offer a deeper examination of bi-level optimization approaches using specifically evolutionary algorithms for accelerating search. This diagram illustrates the scope of our framework, where we enable a validation-only method, a one-shot predictor method, which is quite common in this field of research, and then what we call a lightweight iterative NAS method, or LINUS. In this work, we explore three modalities, specifically the tasks of image classification, machine translation, and recommendations. Now, we do our search using super networks because they offer such a complex search space size. So you can see like 10 to the 19, 10 to the 15. These are really deep search spaces and are really interesting from a research perspective. And one thing to note is that super networks can be encoded in a way that is compatible with evolutionary search algorithms, as shown by the two figures on the right. Now, one example of a super network is this once-for-all MobileNet v3 super network. And so the way it's trained is using elastic kernel mechanism with progressive shrinking on the kernel size, expansion ratio, and layers per block. And the great thing about this is that you get 10 to the 19 unique subnetworks. And so when we consider a multi-objective optimization task, like say top one accuracy and latency, this offers a lot of interesting options for optimization. In addition to validation-only or one-shot predictor approaches, we include a bi-level optimization approach, LINUS, since we are interested in being very sample efficient during NAS in this multi-objective setting. And the important insight is that lightly trained predictors yield useful information for ranking subnetworks. So by iteratively validating architectures, which are suggested by this inner prediction loop, we show that multi-objective NAS can be rapidly accelerated in the three modalities that we are examining. In our image classification experiments, we show how LINUS with NSGA2 for that internal prediction loop compares against random search and standard NSGA2. And you can see with LINUS this really nicely accelerated progression towards a Pareto optimal region in the upper left figure. In addition to this, we also looked at various evolutionary algorithms and how they performed with and without LINUS. Details of the algorithmic settings and additional ablation studies are in the paper. The top set of figures shows that even though we know latency characteristics differ a lot between hardware platforms, the search algorithm performance itself is fairly consistent. In the next row, it becomes pretty apparent that the search-based modality has a strong influence on the hypervolume progression for the various search methods. Given the characteristics of the transformer and NCF objective spaces, the LINUS and NSGA2 results are a little less differentiated from random search than they are in the image classification cases. And so we found that since the distribution of subnetworks in these particular supernetworks are more constrained in both range and occur closer to an optimal region, one would more likely randomly find a good performing subnetwork than in the image classification cases. We described the generalizable NAS framework for multi-objective hardware-aware optimization and performed a deep exploration of evolutionary algorithms using this framework. We highlight the importance of understanding how different NAS approaches perform for different modalities. And finally, we want to recognize thematically similar related work and note that bi-level optimization continues to be a very promising approach for complex search spaces. Thank you.